Hello, everyone. In this video, we're going to continue our notes on section 2.3 and 2.4 by looking at the more derivative formulas in our notes. So in the previous example and video you just watched and did, we computed the derivative of tangent of x. So what we did was we rewrote tangent of x in terms of sines and cosines. And then we were able to deploy the quotient rule in order to compute the derivative, and we got secant squared. So with my more derivative formulas, we can go ahead and fill in the derivative of tangent of x as secant squared x. So now we see that we want to write shortcut formulas for other trig functions. So that is secant x, cotangent x, and cosecant x. Now, similar as we did the previous example in computing derivative of tangent, we could go through and compute derivatives of each of these terms. For example, for secant, we could rewrite secant as 1 over cosine, and then compute the derivative here using the quotient rule. And if we did that, we would get in the end that the derivative is equal to secant x times tangent x. And then we could do that with each of these terms. So cotangent of x is equal to cosine over sine. And then recall cosecant is equal to 1 over sine x. So rather than do this here, I'll just share with you the shortcut formulas. If you'd like to work those derivatives out on your own, I highly encourage it. It would be some great practice for you. But if you want to check your answers, I'll write them out here. So the derivative of cotangent becomes negative cosecant squared of x. And then the derivative of cosecant becomes negative cosecant x times cotangent x. So it's tempting to memorize these formulas, and if you want to do that, that's fine. You can also know that if you are ever asked to compute a derivative of one of these terms or of one of these trig functions, you could always resort to rewriting the function in terms of sines and cosines and computing the derivative yourself. But let's now look together at an example of using these new shortcut formulas. All right, so in example 4, we're told to let y equal secant x over c plus x e to the x. And we want to calculate the derivative with respect to x. So one thing to note here is that the c, since we're taking the derivative with respect to x, we're treating this c just as a fixed constant. So it might as well be 1, 2, just some fixed number. So just keep that in mind when we're computing the derivative. All right, so at this point, I'd like you to pause the video and set up the derivative of this function. So keep in mind that overall, what's happening in this function is we have a quotient going on. So we want to use the quotient rule. So try to write out that formula, and then we'll compare answers together. All right, let's do it. So using the quotient rule, we're going to write the derivative of y with respect to x is going to be, recall, high and low. You all know it now. Low d high minus high d low over low low. Sometimes my lows or my L's and H's look similar, so we'll clean that up. Over low, low. Okay, so let's do it. So our low function here is c plus x e to the x times the derivative of secant x minus high function secant x times the derivative of our low function, c plus x e to the x, all over c plus x e to the x squared. All right, we're going to erase a little bit so that we have a little bit more room. Okay. Awesome. So now there's two parts here that we need to compute derivatives of. And we already kind of computed, in a sense, the derivative of this entire function. But now we just have kind of smaller chunks that we're still chipping away at. So we need the derivative of secant. So we can see the derivative of secant up here. So we need to fill that in here. So we would write derivative of secant is secant x times tangent of x. And then we need to take derivative of this term. So here we have a sum where our first term is a constant. So the derivative would just be 0 there. And then notice we need to compute the derivative of x e to the x. So I'm going to kind of zoom in on that. Oh, literally, yes, zoom in. Okay. So we need the derivative with respect to x of x times e to the x. Okay, so what kind of function do we have here? We have a product. So we need to use the product rule. Awesome, we're getting so much great practice. So the product rule says we compute the derivative of the first term. So the derivative of x times the second term, or second function, plus the first function times the derivative of the second function. So now we can compute the derivative of each part that we need here. So x prime, so the derivative of x is just going to be 1. And we can see that as a power. The 1 comes down, 1 minus 1 is 0. So x to the 0 is just 1. So we have 1 times e to the x plus x times the derivative of e to the x. Well, e to the x is that really special function where the derivative is equal to itself. So the derivative would be e to the x. Okay, so what do we have here? Let's clean this up a bit. So we have 1 times e to the x, it's just e to the x, plus x e to the x. So the derivative of that term here just becomes e to the x plus x e to the x. Okay, so where did that come from? It's really good just to pay attention to the details and take it slow. It came from right over here. So that then derivative, as we move that derivative in, is e to the x plus x e to the x. Okay. It's looking a little messy, but we can just take it step by step here. So now I've computed those two derivatives that we've needed to eliminate all the derivatives involved in our formula. So now let's just gather what we have. So I still have that first c plus x e to the x. So that is c plus x e to the x times secant x times tangent x minus, now I'm on that next term, secant x times, so again, we don't have that 0. We don't need to include the 0. Adding 0 does nothing for us. Times, now we have this term, e to the x plus x e to the x. Then we're going to divide all of that by c plus x e to the x squared. Cool. Okay, are we done? All right, you might be thinking that we want to simplify this because it looks like a mess. But if we notice, we don't have a whole lot we can combine or simplify. If we multiply this out here, then we just have some terms with e to the x's. So those don't really cancel out. We could factor out a secant, but then we just have a product that we get. So essentially, this is our final answer. So the derivative, oops, let's get back the pen. The derivative of y with respect to x is equal to this nice, big, lovely quotient. All right, nice work, everyone. Some of these do get a little messy, but again, it's just about focusing in on, or rather coming from the outside in. So outside, if we summarize, we had a quotient. Okay, no big deal. We know how to handle that. We set up that quotient structure. Now we have smaller or subderivatives we need to compute. Okay, so we zoom in on those derivatives. Okay, then we move back and think, okay, where do these smaller derivatives fit in? Let's write them all out. And there we go. We get our solution. Awesome. Great work, everyone. The more of these that you do, the more familiar you will be with them. So embrace the struggle. We only learn through challenging problems. All right, keep up the hard work.